of lipids is the triglycerides. So triglycerides, this name actually makes sense. This is the block diagram. You'll have a glycerol backbone, and then you have three fatty acids. So again, these fatty acids are carboxylic acids. Glycerol is an alcohol that has three OH groups. We call it a triol. It's a triol. It's got three OH groups over here, and all you have happening is that same reaction that we showed before. It's an ester formation. You're going to remove water, and you're going to do that 3 times in order to make this triglyceride. So I'm going to remove H and OH across this bond. This is where they're forming, and you end up with an ester. You have 3 esters. Here's my ester group here. 1, 2, 3. You don't break the bonds on the alcohol, so this trial stays the same, and then that's the block diagram. So you get glycerol with 3 fatty acids, 3 for triglyceride because you have that glycerol backbone, and you just have 3 esters. Fats versus oils. So fats are going to have more saturated fatty acids. These are when you have like the single bonds, so you don't have any double bonds in there. They're going to have higher melting points because they have, remember, they can pack a little tighter. They're going to have more interaction. They're going to have stronger intermolecular forces, and that's going to give them higher melting points, and that will make them a solid at room temperature. Versus something like vegetable oils are going to have a lot of unsaturated fatty acids. You're going to have these double bonds. It's going to make it kind of kinky. They're not going to be able to pack as tightly. You have weaker intermolecular forces, and so you're going to have a lower melting point, and then it'll be a liquid at room temperature. Can we draw some of these? If we're giving you, if you're given 3 fatty acids, can you draw what that triglyceride might look like? You're going to have triglycerides. So you're going to have that glycerol backbone, and then you're going to react each one of these with, these are your carboxylic acids. So again, just to review that, we have a C double bond O with an H, and then you're going to react that with one of the OH groups on the glycerol, and you're going to remove that H and OH, and so you'll end up with C double bond O, O, C, and you're going to see that 3 times, right? You're going to have an O with the C double bond O. This is what we're building to form that triglycerol, and then this will be the glycerol backbone. This is just a shorthand version of what we're trying to do. All right, so let's work on that. So these are just written out. You don't have to worry about if there's double bonds or what's going on with those. You can just copy those. C13H27. Sometimes I'll give you those where they're actually written out like in this form. This is just kind of condensed for simplicity here. So I have C13H27, C double bond O with an OH. We'll write it all out and then we'll finalize it. H23, C double bond O with an OH, and then C17, H35, C double bond O, OH. So each one of those is going to react with an OH on this glycerol, and you're going to end up with an ester. So the ester is going to look like, I'm going to remove the H and OH, removing the H and the OH across the bonds, I end up with C13H27, C double bond O with an O and a C, C11H23, C double bond O with an O and a C. I'm going to connect those C's. This one's going to have H2, this one's going to have H. C17H35, C double bond O with an O and a CH2. And so that's your ester. You're going to see those ester linkages here, here, and here. And you have a glycerol backbone with 3 fatty acids. So when we're talking about triglycerides, I want you to visualize this. You got a glycerol with 3 fatty acids. These lines connecting them are ester linkages. That's that C double bond O with an O. Triglycerides, their primary role is to provide energy. These are energy storage. You're storing energy, storing those fats in this triglyceride compound. Gram per gram basis, you're going to get twice as many calories as you would from carbohydrates and proteins. These are generally stored in your adipose tissue. These are your fat cells. That's how we store our energy. So provide energy. That is like the main storage energy storage in adipose tissue. Other things that you'll see, so what else do fats do? Thermal insulation, buoyancy, and padding. So this is also, padding's good, it's going to be like a layer of fat surrounding your internal organs. Cushion it against some kind of a blow, protects your internal organs. So that's good. And then like penguins and things that need to keep warm or need to be buoyant are going to also have quite a lot of triglycerides in their body to help them do that. So those are the four biological functions. What are some important reactions? And we've seen all these reactions before. So I like the way this class is kind of built because you learn the general chemistry, then you learn some organic and these reactions, and then you apply those same reactions. We've seen hydrogenation, we've seen oxidation, and saponification is just a hydrolysis reaction under basic conditions. So we've seen these three important reactions before. Now we're going to apply them to some biochemical compounds, so in this case, lipids. So catalytic hydrogenation, that's when you take an alkene, alkene has a double bond, and you're going to add hydrogen across that bond in order to get an alkane. So this is going to take something like an unsaturated fatty acid, and you're going to saturate it with hydrogen. You're going to give each one of those carbons as many hydrogens as they can handle. So you're going to go from a poly unsaturated hydrocarbon to a saturated carbon, the saturated fatty acid. So we've seen this before. We're going to break that double bond. So we'll still keep one of the bonds. We're going to break that double bond and we're going to add H and H across that bond. So our products are it's just going to go from an alkene to an alkane. There we go, hydrogenation. There we go, catalytic hydrogenation. This is also a reduction reaction. We'll look at an oxidation reaction, reduction reaction here. You're increasing the number of CH bonds. And catalytic just means it has a catalyst. We're going to use the platinum catalyst in order to do this, to produce some saturated alkanes. Here's an example of a fatty acid. So here's our triglyceride. Notice we have the we have our ester linkages here. We're not breaking those. In this reaction, we're just focusing on the double bonds, and we are adding hydrogen across those double bonds so that we're basically breaking the double bond, turning them into single bonds. So we're adding hydrogen across all of those. We end up with saturated fatty acid here. So this is unsaturated, and then this one over here is saturated. So this is saturated, this is unsaturated. Unsaturated means you have double bonds. Saturated means each one of those double bonds, each one of those carbons is saturated. They're soaked with as much hydrogen as they possibly can get. You can also have partially hydrogenated, where not every single one of your double bonds gets converted into a single bond. You can have partially hydrogenated vegetable oils, maybe you've heard of that. And during this process, some of the double bonds are converted from cis to trans, and not all of them. So not all of them are turned, some are turned from double bond to single bond. You can also turn some of these cis to trans. Now you have trans fatty acids. You may have heard that those are bad. When you partially hydrogenate some of these oils, you get like a semi-solid consistency, which is generally good for cooking. What's good about it is that, it is good for cooking. The consistency of it is more like a saturated fat, but since it doesn't come from an animal, it doesn't come from the animal sources, you don't have the cholesterol in it. So when you get the saturated fats from animal sources, they're going to have cholesterol, and that's going to be bad. You don't want to have too much cholesterol. Partially hydrogenated vegetable oils, these are sometimes used in shortening or in margarine, and a lot of other sources as well. So the good part about it is that your consistency is like saturated fatty acids, but you don't have the cholesterol in it. That's a good part. Having fewer carbon-carbon double bonds in the partially hydrogenated oil also makes it not spoil as fast. So if you don't have all these double bonds, it will minimize some of the auto-oxidation reactions. So these can oxidize, they can break down, and then that's how you get like rancid butter. So if you can minimize those double bonds and make them single bonds, then it'll last longer. It'll have a higher shelf life. That was one reaction. So catalytic hydrogenation, which is a reduction reaction. The opposite of that is an oxidation. So auto-oxidation is when this thing like just reacts with the oxygen in the air. Like you don't even have to make this happen. It just happens. So if you leave butter out for a long time, or not even that long, but for a certain amount of time, it will start reacting with the oxygen in the air and it'll start breaking down. And so this is what gives, makes has a very unpleasant odor. This is what spoils your butter. So if you reduce the number of alkenes, in your systems by partially hydrogenating it, or if you keep it cold, or if you keep it capped. So if you can keep your butter out, just put it under a dish so that it doesn't react, under one of those butter dishes, so it doesn't react with the oxygen in the air and spoil and oxidize. Then it'll be fine. It'll last fine. It'll last longer. And then the last reaction is saponification, and we've already kind of looked at this. This is the ester hydrolysis, but in the presence of a base. So as I mentioned before, saponification is how we make soap. So this is used in the production of soap. Soap is kind of cool. It's amphipathic, which means one side is hydrophilic, one side is hydrophobic, and they form these micelles where the hydrophobic region is going to be on the inside of the sphere, and the hydrophilic region is going to be on the outside. I don't think I have any pictures. You can change the properties of soap by changing which base you react it with. So again, saponification, just hydrolysis. We're going to add water. We're going to break apart an ester so that we get, instead of getting a carboxylic acid and an alcohol, we're going to get the conjugate base of that carboxylic acid and the alcohol. So you can change the liquid by, I'm sorry, you can change the soap by the properties by adding sodium hydroxide or potassium hydroxide. Sodium hydroxide is going to give you a solid soap. Potassium hydroxide will give you more of a liquid soap. And so that's just how they make soap. The greater unsaturation also produces a softer soap. So you can change the fatty acids and you can change the base that you're using in order to manipulate the properties of the soap that you're trying to get. So hydrolysis is important for also important for the digestions of fats and oils. This is going to happen in the small intestine. We're going to talk more about this when we talk about digestive enzymes. But you can break this down. So how do I take this fatty acid and break it down? You can break those ester bonds here. We're going to break those. You'll get the glycerol back. That's going to come back unharmed. And then instead of having the acids that we started with, you're going to have the conjugate bases of those acids. So again, this is because you're under basic conditions. So the carboxylic acid can't exist under basic conditions. The conjugate base of that is going to dominate. So you'll get the conjugate base of these. These are going to be pretty soluble because now they're ionic. Remember, the whole point of reacting these with the base is to make it ionic instead of the carboxylic acid. The ionic form is going to be more soluble. Sorry, there's the picture I was looking for. Okay, so we've got a non-polar head, we've got a polar tail. So this is what a micelle looks like. So the dirt's going to be in the middle there because dirt, that oil, that grease, those are all non-polar things. Those are going to be like your fatty acids. They're going to talk to your fatty acids. And then the outside is the part that talks to the water. So the hydrophilic region of the soap will be on the outside. So soap's going to look like this. You're going to have a non-polar region. You're going to have a polar region. The polar part's going to talk to the water, or the ionic part's going to talk to the water. And then it kind of forms this little ball around the dirt particle in the middle. So we say soap is amphipathic. That's a great word to know. Amphipathic. Pathic is really just talking about, does it like water or does it like not like water? Is it hydrophilic, hydrophobic? Amphi means both. So part of this soap molecule is polar or ionic. It's hydrophilic, and then the other part is hydrophobic, where you have that long hydrocarbon tail. Yep, and so that's how soap cleans things. So the grease is going to talk to the hydrophobic region of the soap, and then the hydrophilic part will talk to the water, and they'll be able to wash it away. Cool. So can we draw the products of a triglyceride? So we already did it for just a regular ester. Can we find the products when a triglyceride is saponified? So I'm going to tell you what we're going to get back out of this. So remember what a triglyceride has. Let me go back over to our block diagram for a triglyceride. Whoa, way back over here. You have a glycerol and then you have 3 fatty acids. So what we're going to get out of here is we're going to break those 3 ester linkages. Glycerol is going to be unharmed. And then instead of getting the 3 fatty acids, we're going to get the conjugate bases of those fatty acids. So let's see what we get. So I'm going to break those ester linkages, break these bonds here. Boom, boom, boom. I'm going to end up with glycerol. Glycerol is going to be our standard. He's not going to be changed. That's my glycerol. It's a triol. It's an alcohol with 3 OH groups on it. And then I'm going to get this guy out of here. Again, hydrolysis, saponification is just hydrolysis, like adding water, adding H and OH across this bond. I'm going to add H here, and I'm going to add an OH over here. But because we're under basic conditions, that H is not going to stay. I'm going to get the conjugate base of that carboxylic acid. Have this instead. Same thing here. I'll have CH3. CH2 14 with a C double bond O and an O minus, and CH3, CH2 16, C double bond O with an O minus. So I'm going to get those 3 conjugate bases of the carboxylic acids as well as the glycerol. Glycerol, these hydrogens are not pH dependent. They're always going to be there. It's an alcohol. The carboxylic acid is acidic, so under acidic conditions, the hydrogen will be there. Under basic conditions, it won't be there. All right. Two questions here. Which of the following reactions is responsible for the smell of rancid butter? So remember, hydrogenation, you're taking an alkene, adding the hydrogen across that bond. Saponification, that's an ester hydrolysis. Autooxidation. Autooxidation is when you are, that's what happens when butter goes bad. So if you leave it out in oxygen, it starts to react with the compound and starts breaking it down. So here's our autooxidation. So you're taking all these long chain fatty acids. You get your it starts breaking them up into smaller pieces. So you can get an aldehyde, you can get these, another aldehyde, carboxylic acids. Um, that's the part that happens there. So that's the autooxidation. That's what's responsible for rancid butter. Which of the following reactions can raise the boiling point of triglycerides and make them more solid? All right, well, how would that happen? What makes a better solid when you have unsaturated fatty acids or when you have saturated fatty acids? So when you have saturated fatty acids, that's going to increase the boiling point. That's going to make it more, or increase the melting point. That's going to make it more solid. So if something undergoes a hydrogenation where you take those double bonds and you turn them all into single bonds, and now you're adding hydrogen all over the place, right? Now we're going to have way more hydrogen on those. You're saturating it with hydrogen. You're going to turn an unsaturated fatty acid into a saturated fatty acid. That's going to increase the boiling point and make this more solid, boiling and melting points. So hydrogenation. So if I added H2 across these bonds, that's going to increase the boiling point or melting point. Cool. So then trans fats. Now you've heard about trans fats before, probably. You have unsaturated vegetable oils are partially hydrogenated. So in that process, sometimes the cis double bonds are converted to trans. So you can turn from cis to trans, even though for the unsaturated, all you're doing is adding hydrogen across those bonds. Sometimes it doesn't add completely, and then it just instead you have an isomerization reaction where you go from the cis isomer to the trans isomer. And the trans isomers are going to pack tighter. They're going to pack a little bit better than the cis isomers. If you have so we'll call that partially hydrogenated. I mean, not you still have some unsaturated fatty acids in there. So partially just means some of those double bonds underwent the hydrogenation process. Diets that are high in trans fats, this is going to be bad for your cholesterol. A lot of times these are linked to lower HDL. HDL is the good cholesterol, so you have less of the good cholesterol. It could also make changes in your membrane structure. So we'll look at the lipid bilayer at the very last section. We'll look at how does that change when you have lots of saturated versus unsaturated, and then if you have trans fats in there, how does that change things? Nutritional labels. So if you look at the nutrition labels, they will tell you how much trans fats are in your food. So it'll say fats, and then it'll say fats from like trans fats. A lot of cities and states ban the use of these trans fats in elementary school or high schools and school cafeterias. Ban the use or try to minimize the use of those. And a lot of fast food restaurants stopped using these trans fats because they were not good. Some trans fats are naturally present in beef and dairy. So you'll see those in milk and butter and cheese. So some are naturally occurring trans fats in your system. And And the last one I wanted to point out was olestra. Olestra is a sucrose ester. So what they did is they made this fat that basically your body can't break down, and they put it in chips, and everybody loved them because they were like fat-free chips. There's no calories in the diet because your body just doesn't have the enzymes to break it down. So they modified this is a sucrose molecule. They put ester groups on there. So you can see up there, that's where your fatty groups are. And then your body can't break this, your body just can't break it down. So you would eat these chips, there's no calories. And they're banned now, so it's called wow chips. There were a lot of digestive issues that people were having after consuming these chips. They're no longer around.